sessions, it was in 2 different cells. Now those 2 different cells will be moved to the class method. That's it. So we implemented underscore backward and build topo methods. Underscore backward again to calculate the gradients and to assign the values. Build topo for topological traversal of the node graph. Now code is in separate cells. We have to make it part of the value class. That's the only thing. So it was there in the subsequent cells, we just have to push it up back to the value class. So why this code change? Again, I already mentioned it is for better code readability and maintenance. And this is a short in-class activity for you to warm up. 5 minutes is the time I give you. The reason I am giving you only 5 minutes is because you already have the code. Build topo and backward is something not alien to you. You already implemented that. And for loop is also implemented. What you do is you copy paste and put the code in the value class under a method named backward. So def backward parenthesis colon followed by the code which we already implemented. I give you 5 minutes for that. Anyone who is done with that task can show it to me and then I'll give you a solution. I'll pause for 5 minutes. What will happen anyway? The code will be given. No, don't have that attitude. Please do it.
Please open up your workbooks, the playground, in your Tantric. Just log into your Tantric. By the way, there is no copy paste anyhow. You need to type it. Yeah, by the way, anybody could copy paste? Did you copy pasted anything in the Tantric? It's okay. So we will not penalize anything. We want to know. I want to see the cracks, the robustness of the system. I said you can't copy paste. If you can copy paste, please let me know.
So up to this point, you already have the code here, the value class, where we use this underscore backward. You implemented that as part of the d underscore methods. This code was already shared with you. You completed an assignment. Then we implemented this cell, where we did a topological sort, build topo. And then we have a sequential call of backward on all the nodes from right to left. So I am saying that whatever code is there in this cell and this next cell, it has to be moved to this backward method. That is the only task. Method signature I gave you, but there is something missing in the method signature also. So 5 minutes I'll give you and quickly show me the code. There's nothing new, it's just refactoring your code, reorganizing it, that's it.
Yes, Sripooja, can you zoom a little bit because yes, thank you.
So if anyone has already completed the code, you can raise your hand. We'll quickly come around and check the code.
Yeah, Sripooja, practice notebook for this is started.
The old practice notebook, they
Old
can
one.
use that. Yeah.
Yeah, you can use the old one. You can open the previous practice notebook and code it. Practice notebook will be continuously the same. Yeah, I have a small question to most of you. For the forward feed, Sripooja is using an activation function. Which activation function are you using? How many of you know it is ReLU? How many of you know it is sigmoid? No. How many of you know it is tanh? Sit down, please. Yeah. So we are using tanh. So when I asked few, nobody could answer. So we are using tanh. Please remember why are we using activation function and which activation function you are using it. Okay. Okay, one more question here. If I am using tanh, what is the range of tanh? -1 to +1, correct? If I have a weight of -6 or +6, what will happen? So it will be in 1 or -1, right? Within the range, correct? Yes? Am I correct? Or is a negative weight have an effect on tanh activation function? Does a negative weight have an effect on tanh activation function? What does bias do on tanh activation function? If you change bias from 0 to +5 or +10 or minus, what happens? What changes happen? What happens with the respect to bias? What happens to the activation? What activation function will do to your data. Yes?
Vishal, the value explodes. It goes up.
Goes off the curve. It creates an offset. Okay. Okay, strange. One. Not exactly correct, but yes. Okay. Just hold on. Yeah, just look at this visualizer. We'll understand what I was talking about. Can you zoom a little bit? Yeah. So since this is a linear, I'm not worried about this. Just select tanh. Zoom a little bit out. So that is a tanh curve. Now there is weight, right? If I go to positive, see the graph, what happens? Positive values. If I expand positive value, it compresses and it tries to accommodate. And if it is negative, just see, it inverts itself. This is the effect of negative weights and positive. Let us do for bias now. Now let's change bias to the positive. See there. You see this? This is the offset which is happening. Just now negative bias, it goes to plus offset. Right? So this is what you should have when you are trying to train. Because when you go to train this model, you will understand the importance. Yeah. So if you're just unfreeze, if you know what the visual aspect, if there is a node given, based on that, you will know how training data will superimpose, how your training data will superimpose with the actual data set, how it tries to get closer the loss values and all. Okay? That is very important. It should align with the training data set based on the activation function. We'll see all these things later. That is a higher aspect. Yeah, Sripooja, you can just close it.
So anyone done with the code? No? Yes, no? Raise your hand if it's done.
Now, if you are done, please show us the code. Okay, since it is a activity, in-class activity, if you are still struggling, let's learn now.
So,
Let's learn.
Yes, so this is what I had asked you to implement. And this is something that we already did, C equal to A plus B, etc. Then we have code for automatic back propagation. That is to build topology first, and after that we call the backward, which is going to assign, calculate the gradients and assign the values. Now coming to the solution, the method that you have to implement is this backward, and what it takes is self, because you're calling backward on the same node, right? So self, and then you have topo list, which we already discussed, so I won't be going through this. So I'll highlight only the changes that are required. So this takes self, and now you assign the gradient for self. So what we did earlier was we assigned the gradient value for C, which is the output node. Now in this case, wherever I am calling the backward function, that becomes the output node. So that's the reason I am assigning self.grad is equal to 1.0, because gradient of any value with respect to itself is 1. After that, I call the build topo function, which we previously defined here. So this method is as it is. It takes the parameter v, whatever values we pass to it, from there it starts building the topology. Now I am calling that build topo on self instead of calling it on C. So that is one change. After that, this is again the same method. Nothing changed here. The only place where things change is backward takes self. After that, you initialize gradient for self, and then you build topology on self. So these are the only 3 places where you need to change your code. Remaining everything, the logic, everything is same. Even the variable names that I use, the argument names or parameters that I use, everything is same. So this is the backward method that we implemented now as part of the value class. And what will I get out of this is it is only for code maintainability, that's it. And I wanted you all to get started with the target section today again. That's the reason I gave you this in-class activity. And again, you'll be using this for assignment. So please make a note if you haven't implemented this code, or if there's something buggy at your end, please take some time, fix the code. So now it's done. Anything pending? And please be careful of the indentation, because we are nesting a lot of methods, the loops, etc. So indentation, you have to be mindful about that.
It's good to understand. There is a very definite objective and purpose why want you to understand this at this level. See, in this edition of deep learning, we are not going to use PyTorch till it becomes inevitable that we have to use it. After we do the linear story, which Pooja will cover, our next sessions will be with CNN. We are not going to use any CNN libraries. You are going to build CNN. You are going to build each part of the network till you reach a complexity which you can't deal. Till then, there is no library. I mean, only library is the Python library. We are not going to fall back to PyTorch. No. Now you say when PyTorch is there, why can't we use PyTorch? Okay, the answer is very simple. We don't want you to become users of PyTorch. That there is many people in the world who know how to use PyTorch. We want you to use or to understand how PyTorch runs. See, you are not going to become only users of libraries. You are going to become creators of libraries. The opportunity is not there. That ChatGPT generates code. You ask it to generate code for a CNN or a network, we don't need you. You have to be very clear where you are needed. Nobody needs you to generate what PyTorch does in 5 minutes. ChatGPT does in 5 minutes, maybe better than what you are able to do. Now, where does the fun come? How do you implement a new kernel in a CNN? That is where your role comes. And we have an expertise to create that kind of a new kernel. The standard kernel any game goes over an image, picks up. That I don't need you to learn. We don't need Tantric, we don't need nothing. Anybody can do that. What is that kernel to be? Open ChatGPT, 2 minutes you know how to do it. But if you have a different algorithm to create, that is what comes here.
Yes. So how many of you have done the activity so that we can move forward? Okay, well, if you have any problem? Any problem you are facing? Yes? Yes? Any problem you are facing? Okay, you are not able to. Okay, you don't have the proper function. Okay. What about here? Done? What is the problem that you are facing? So you want to learn slowly, yes? Okay. Yeah, Sripooja, you can just start. Let's move ahead, and if you have any roadblock, please stop us. Okay?
So this is the code, very simple, but make sure that you don't have these build topo methods in the next cells because it will override the gradients. So in few cases the gradients will again set back to 0. So make sure that build topo and backward is implemented only once and it is called only once. So if everything is clear, then your method should look like this one. Backward self, that is what I explained, and then backward. Now where is the change that you are supposed to do? You have to call backward here, C dot backward. So this is one method call that you have to do, which we did earlier using a for loop. Now if I go back to my old code which is here, what we did was, for each and every node we called a backward method. Right now we simplified it because we have a class method which handles everything, the complexity. So we just are good with C dot backward. So once you do that, you should be able to see this graph, the node graph, which takes two values, A and B, that is 3 and 2, C value is 5, and the gradients flow back. That's because it's a plus operator, quite straightforward. So method class implementation is important. It's to give more structure to your code, nothing else. So if this is done, we move on to the next concept, which is slightly different. As I told you, we'll be dealing with the multiple connections. So I don't want you all to work on the code right now. You can work on it during the assignment because we have the starter code there, so you can explore the code further there. So I need your attention towards the PPT for some time. So this is what we completed, that is just adding a backward method, removing our code from the cells and adding it to the class. Now, as I told you, multiple connections are important. So far whatever we dealt with, they had neurons and a single connection. Meaning we saw that A, B, then C. A has a single connection with C, B also has a single connection with C. But what if there are multiple connections? There is a D, then A has a connection to C, then A has a connection to D. I'll show it to you with the help of visualization, but just to complete the theory I'm telling you. But what if the A node has two outgoing connections? Then what will happen to the gradient? Is it the last one which gets replaced? How should we manage those gradients? We'll understand that in depth with the help of examples and visualization. So from previous session, just to give a quick recap, if we were to do C equal to A plus B, the same thing, then this was the node graph we generated, right? And this is no-brainer, so what are the gradient values? Just to fill up those boxes there. 1. Both the values are 1 or different? Both the values are 1, right? So there is a plus operator which allows the gradients to flow back, so the gradient value is 1. This is in case of a plus operation. Now moving on, we also discussed C equal to A into B, which we noticed that the gradient flow is slightly different because the proportionality changes in case of multiplication operator. So what did my graph look in that case? Again the same thing, but what will be the gradient values? You know you are good with manual calculation of gradient. So what are the values now? First for the gradient of A. Gradient of A in case of multiplication operator is 3 and for B it's 2. So you still remember this, right? Now what we see is B equal to A plus A. So I am not using C this time, I am saying B is equal to A plus A. So what do you think should happen to the gradient? So this is the same node graph, but is there something missing here? There are two variables, they are displayed in the graph, but what is missing according to you? Look at the equation, look at the graph. One more, sorry. One more? Arrow? Yeah, one more arrow, certainly. So in case of plus operator, again this is one more arrow because we are saying B is equal to A plus A. So if you generate a graph using draw dot, it's going to generate arrow one above the other. So you won't be able to see that in a graph. That's the reason I added one more arrow so that we can discuss and visualize this clearly. Now again, I don't want to give the solution, but what do you think should be the gradient in this case? So basically B is equal to 2A. So what is the derivative of B with respect to A? B is equal to 2A, guys. I am asking dB with respect to dA. That is derivative of B with respect to A. 2. So the gradient value should be 2. But what do you think happens with the code that we have right now? Change your code. You have C equal to A plus B. Change it to B equal to A plus A and tell me what is happening to the gradient. You have the code ready, everything is there, you just have to change the values. It's still giving you 1. That means there is a mismatch somewhere. And what do you think is going wrong? Ideally, we should be getting gradient 2, but we are getting 1. Why is that so? Logically, where do you think there is a flaw in the code that we implemented? No. How many methods are there to calculate and assign the gradients? Do we have multiple in case of plus operation? We have a plus operation and we are overwriting how it functions with the help of underscore underscore add underscore underscore. That's a D underscore method for addition. In that you are calculating and assigning the gradients. So how many places are you calculating and assigning the gradients? There's only one place. Logically, there's only one place in your code where you're calculating the gradients and assigning the gradients for a plus operation. Correct or no? Huh. So what do you think is going wrong? Why are we getting gradient value 1 and not 2? I zeroed it down to underscore backward method for you. Go to D underscore addition, you have a nested method underscore backward. There you're doing some calculation and assignment of gradient values. So what do you think is logically wrong in that 2 lines of code? Louder? I'll come there. Yes? Okay, but how will that help us if it's same or different? Okay. Self and other are different. So, but you're looking only at 1:1 connection. What if there are multiple intermediate nodes? A will have multiple connections. So, how many will you keep checking? You're partially correct. Huh, right. If it has an initial gradient, then okay. Okay, let's say, okay, it has some gradient already assigned and you say, you check for it, it has a gradient. Then you see that it has children, further children. So what do you do in that case? Child 1 is giving you gradient 1, that is 1. Child 2 in this case is again B, which is having gradient value 1. So what do you think should happen when there are 2 gradient values? Correct. So basically, if there are multiple connections, you're just going to keep adding the gradients. So what do you think we missed in this case? I gave you the answer, guys. In the logic, what is missing? Just tell me that. Adding gradients is missing, right? So basically, we are calling backward every time, and every time our backward method is overwriting the previously assigned gradient value. We are not depositing the gradients, we are not accumulating the gradients. We are just taking the last call of the gradient and we are just keeping it there. So that is the step that we are missing in our code. So somehow we need to fix it so that we can accumulate all the gradients together, right? With this example, it's clear that the gradient of A is 2. And why is that? Because there are 2 connections between A and B. And every time there is one gradient flowing back, that is 1.0. So 1.0 flows back in the first call, 1.0 flows back in the second call. So what should we do? Addition. So how will you fix your code? It's just 2 lines of code, guys. You already have it. So what do you think has to be added or modified in that code? There are no if, there is nothing else. I'm giving you the hint. Yes, plus equal to. I know these are quite primitive questions, but the reason I'm asking you is because I want you to look at that minute level. If you have this ANN training, everything well set and theoretically, then how do you translate that into code? You have to be clear with that. So if you have pseudocode, then how do you write the code for it? That's the reason I'm asking you these questions. So again, I'll give you the solution, dB of dA. If you do a normal mathematics on paper, if you're doing it, then it gives you 2. So A dot grad should be equal to 2. That is what we said. But where do you think the code should be changed? I gave you a couple of hints. It is underscore backward method that has to be modified. So there is a plus equal to which has to be added. Earlier we used only equal to for assigning the gradients. We were not accumulating the gradients. So that was the only step we missed. That's a flaw in our code, and right now we are fixing it. But why do we fix this code? What is the need? So what are we handling? If I have a plus equal to in my backward method, how is it going to help me? That's the title of my slide, right? Multiple connections. So this is the code change that you have to do, two places. Instead of equal to, you use plus equal to. That's the only change that is desired. We are doing this precisely because we want to handle multiple connections, and in case of multiple connections, there are multiple gradients also flowing back to a single node. And we want to accumulate, keep a note of all the gradients that are flowing back without replacing or substituting them. That's the reason we are including plus equal to instead of equal to for accumulation of gradients. So when I asked you this question, the expected answer is that, ma'am, we are handling multiple connections and we were not accumulating the gradients in the first place. That's the reason we now introduce plus equal to in order to accumulate the gradients. So that is the simple answer you can give. It's there, right, on the PPT slide itself. Now we understood the gradients were getting overwritten, all good. We fixed it in case of addition. Now we fix the backward code. This is working fine for a plus operation. But is addition the only operation that we encountered so far? What are the other operations that we dealt with? Multiplication, tanh, correct? So we used these operations quite frequently. What about those? Now let's consider multiplication. For this I won't give you the code, but in theory I will explain how you should calculate and verify whether your code changes that you do is correct or no. So now we'll slightly take a complex mathematical equation because I want to introduce multiple connections, and it should be easy for you to read and draw a parallel between the node graph and the mathematical equation. So the equation that we are going to consider is f equal to a into b into a plus b. There are only two variables, that is a and b. But I am using these variables multiple times in my mathematical equation. So how will my node graph look in that case? Now quickly do this either in the notebook or take pen and paper, do it and show me how will the graph look for this mathematical equation. You have a practice notebook. I'm still fine if you show it to me in a practice notebook. And feel free to introduce intermediate variables if you want to. Okay, so some of the students have already shown it to me in the notebook, that is in Jupyter notebook, but if you have a notebook where you're taking the notes, if you want to show it on that, that is also fine. So the hint is that introduce intermediate nodes, that is intermediate variables, to store A into B and A plus B. So it becomes easy for you to visualize and understand what's happening in the node graph. So anyone else? Right side the students have shown me, but what about students on my left? Yeah, I'm waiting for one answer from my left side, the students here on my left. One answer and then I'll proceed with the solution. Okay, so two intermediate variables and then finally. Okay. So keep it ready in the notebook. Alright, so most of you have got it because that's we already discussed this. So let's quickly look at the most important part, that is the gradients. So this is how your node graph should look like. You can see this, right? So I said you introduce two intermediate variables for storing A star B, that is A into B, and for storing A plus B. So I introduced two intermediate variables F and E, D and E, and I am storing the final value in F. And because I wanted this picture to be good enough, I had to crop the gradient part of F. But the gradient of F, we know it is 1. Right? Now the fill in the blanks here are all the gradients. So let's fill them one by one. Don't look at the code, not needed. Just look at the slide. Theoretically, let's fill it first. Because you understood what is the problem in the code. You understood that we have to deal with multiple node connections. And we have to accumulate the gradients somehow. Up to that point you understood. Now just take a look at this node graph and help me in theoretically filling what are the gradient values or what should they be. So we will verify one by one. So what should be the gradient of D? It's a multiplication operator. 3. And what about the students on right? Is it 3? Correct? So gradient of D is 3 and E 2, right? Now, and what about the gradient of A? This will take some time. Do the mathematics if needed or calculate in your mind and tell me. 8, okay. And why? So which two gradients are you adding? Because I see only 3 and 2. Okay, you're saying, so I'm just repeating what your friend says. He says there is one gradient which flows back and that is because of the plus operation and it is E dot grad which flows back, good.
Then we add 2 into 6 to 2.
Okay, so he is taking one gradient from the plus operation, that is 2, and in case of a multiplication operation 3 into 2, that is 6. It is 8. Does anyone have any other opinion? Do you think it's wrong? So the reasoning also we discussed. The plus operator gradient flows back as it is, but in case of multiplication what happens is 3 into b dot data, which is 6. So 2 plus 6 is equal to 8, and that is the gradient of node A. So this is in theory. Everything is in theory. Is it clear to you all how are we accumulating the gradients? If it is not, then the next exercise will become tough. That's the reason I'm spending as much time as possible. And this visualization has to be very clear in your minds. So I'll give you 2 more minutes if you want to solve it on paper, or if you want to solve it on Jupyter Notebook, please go ahead, do it. Okay guys, so most of you have understood what's the logic, what's happening. I can clearly understand from whatever your friends are saying and the way you're discussing. So we'll not waste further time, we'll waste more time on the assignment, we'll rather spend the time there. So a similar code is required in case of multiplication as well. For the in-class activity, what we saw is the code change in the backward method of addition operation. The underscore method of addition is what we modified, or I showed it in the PPT. But the same or similar code changes have to happen in the case of multiplication as well. So that is as part of your assignment, I want you to work on it. So I don't give the solution here. So do it in the assignment. But again, I think Neil sir already answered this question. Why should you all know this, right? Or the kind of questions or the question mark that we can, the implied question from your expressions is that Hugging Face is anyway giving us the pre-trained model. So why should I go through all this stuff? Why should I understand the mathematics? So this is a general kind of questions you ask. Some are bold enough to ask. Some still have it in their mind and face us. So that's the reason I included this question. And the answer is you should know how to tweak the models. Because general models, the pre-trained models solve the general solutions. The general problems are solved using the general pre-trained models. But if you're working for a company or in an industry or any open source project, you work on specific problems. So you should know how to take these general models which are pre-trained, and then you have to tweak these models to fit your requirements. And that is exactly what is going to pay you. It's going to give you an edge over other software engineers, or that is the part which needs innovation or thinking. So that is the answer. Now coming to exercise 1, we have this exercise on Tantric. It's the same thing, dealing with the back propagation in the case of multiple connections. And solution graph is clearly depicted in the notebook. I will enable the notebook in some time. So just understand that you still have to solve this problem for multiplication as well. So do you see this notebook now? Week 2, day 1, exercise 1.
Can you open the students' view and able to access the notebook? The exercise 1. Sripooja, can you just open the student version?
Are you able to fetch the notebook or no? No?
The exercise 1. Day. What is the name of the exercise, Sripooja? Day?
Week 2, day 1.
Yeah, week 2, day 1. No? Just refresh. Can you just refresh? Yeah, now just refresh your screens and open up, fetch the notebook. And write the code.
So this is the student view that you should be able to see now. We named the notebook as week 2, day 1, exercise 1. So week 2 is the main prefix that you have to look at, and day 1. So what is expected is the final solution should look like this. So you are well aware of how to assign the values using the value class. A, B is already there. Then I am giving you some intermediate variables D and E. So what has to be done? Everything you have to implement. Now this is the general cell that we use, and here coming to the value class, you have to implement the backward method. You have to initialize it here correctly, and then I'm giving you the basic signature of the backward method in the D underscore methods, that is under addition, you have to implement this. Under multiplication also you have to implement the backward method. Tan H also you need to implement the backward method, but again we won't be having any assertions on tan H right now. Now the backward method that I told you as part of the in-class activity, we already discussed. So in order to save your time, I am giving you some boilerplate code already. So just focus on the logical part here. How do you build the topology and how do you call the backward method here? So the starter code is already there for you. I left the code where it needs your logical understanding, that has to be filled in. Now once you do this, all the initialization, I am giving it to you directly. So you don't have to worry about how to initialize the variables, what are the variable names, nothing has to be bothered about. So I am calling the backward method here, and then I am building a graph. And these are the assertions here. So if you are having the correct implementation of build topo and these backward methods, the nested backward methods, if everything is right, then the